We got to learn how to find a linear function that can approximate our data point, and we did some examples on that. But with the concept of least square regression, we want to minimize the summation of error squared. Let's look at the next situation. Assuming that I have a set of data points and I sketch the graph or locate all the points on my xy plane, and I have that graph. So it looks like over here I have a quadratic relationship between data points. So it's not a good idea to find a linear function to approximate this set of data points when you see it clearly that the relationship between the data points is pretty much like a quadratic relationship. So if we are under the same concept, we want to minimize the summation of error square, and we want to find a second degree polynomial that can be used to approximate the data out of this situation. That means we want to find the look of the polynomial equation of second degree a plus bx plus cx squared. So we want to find this guy that can be used to approximate the data point. The concept is the same because we want to minimize the summation of the square of the error. Let me define the error epsilon sub I as the difference between the exact value and the approximate value. The exact value is each yi, and the approximate value is going to be p at si, which is a plus bsi plus csi squared. So that is the error for each I. But I want to square everything, okay? So I square the error. So on right hand side, I put the brackets, cover the difference, and square it. But I want to minimize the summation of the square of the error. So I add them all up. Summation of epsilon sub I squared, and I runs from 1 to n because we have n data points altogether. So the summation must be from 1 to n. And we do the same thing on the right hand side. We take the summation when I runs from 1 to n, add all the errors of n data points together. I start from 1 and stop at n. And you copy this right over. You want to minimize this guy. You want to minimize the summation of the square of the error. So what is the concept here? You want to minimize, that means you want to find a, b, and c such that this p, this polynomial, will give you the minimum value of the summation of epsilon sub I squared, or summation of error squared. So a, b, and c are to be determined. So you need to differentiate this once with respect to a, once with respect to the b, once with respect to the c, and set those three equations as 0. Okay, and then you can get yourself a system of normal equations, exact same manner as when you were finding a linear function. Okay, but you have more work to do. You have more equations involved. In this case, because you have 3 constants to be determined. So I leave that for you to practice yourself of the way of deriving the system of normal equation. But I put the summary for you in the next slide of the look of the system of normal equations in the case that you want to find a polynomial equation of second degree. So that system of normal equations consists of 3 equations and 3 unknowns, and the 3 unknowns are a, b, and c. And it looks like from the coefficient matrix, we have to have the column in our table that gives us summation of si squared, summation of si cubed, all the way to summation of si to the power 4. And on the right hand side, not only you need summation of yi and summation of the product of si and yi, you also need the summation of si squared times yi. Okay, so your table is going to be larger than the case that you used a linear function to approximate your data. And we're going to be seeing some example in using least square quadratic to get the approximation or second degree polynomial to approximate our data. In the example 10.3, we want to find the standard least square parabola for the data in this table. So we want the parabola. The parabola is a second degree polynomial, or you can say p of x equals a plus bx plus cx to the second. So by using all the data points, that we have 8 points altogether, we would like to find the constants a, b, and c such that this second degree polynomial will give us the approximation that we can minimize the summation of error square. Alright, so based on the system of normal equations in the previous slide, we need to solve a system of 3 by 3 because we need to find the values of a, b, and c. So our system of normal equations will have 3 equations and 3 unknowns. The 3 unknowns to be found are a, b, and c. So it looks like from the coefficient matrix, we need summation of si, summation of si squared, summation of si cubed, and summation of si to the power 4. That's why I constructed a table of this example that my first column has si, second column has yi, and I need the columns of si squared, si cubed, and si to the power 4. Now let's look back to the right hand side of my system. I need summation of yi. I have the column of yi already in my table. I need to have the summation of the product of si and yi, and I have that column in my table as well. And I also need this guy, summation of the product of si squared and yi. I did not need this when I was working with the linear regression polynomial, because that at that time it was only for linear regression, but this time it's for the second degree polynomial. So we need the column of the product of si squared and yi. So I have that column. So I use Microsoft Excel to get this table. When you do your test, it's okay with me to use Microsoft Excel to get the table like this, and you add those values of s together by using the command in your Microsoft Excel. Summation of si squared, you can get it by using Excel as well. Okay, so with that table, I get everything I need. Then, by using that formula in the previous box, okay, I can then have the system of 3 equations and 3 unknowns. In this spot, we put n. In this case, n is 8 because there are 8 data points altogether in the table. That spot is for putting summation of si, which is 20, summation of si squared, which is 92. That spot is summation of si squared, and this is summation of si cubed, which is from the table, is 440. That spot is for summation of si to the power 4, which is 2276. Okay, the right hand side, we put summation of yi, summation of the product of si and yi, and summation of si squared times yi goes in that spot. And then keep in mind that you have to find a, b, and c. So you are to solve this system for a, b, and c. Over here, I did not show you the way to get a, b, and c. I just say that the solution to this system is this guy. A equals that number, b equals that number, and c equals that number. But when you do your final examination, I need to see all the steps in solving this system. You can use Gaussian elimination or whatever technique as long as you can solve the system and show me the details of the work, how to get a, b, and c. Alright? And after you've got the values of a, b, and c by solving that system, then you obtain the second degree polynomial that you can use it to approximate the value of y at any value of x. And with this second degree polynomial, I can guarantee you that the summation of error square will be minimum. Back to the question asks us to find the approximate value of y at s equals 3.5. And s equals 3.5 is off the table, it's not in the table. Okay, so you can use that second degree polynomial to approximate y value at the point s equals 3.5, which is not in the table, and we got the approximated value as 0.7857. Okay, out of this table I did not have the column of the table that gives you the sum of error square because the question did not ask us on that. So when you do your final examination, you have to read very carefully what is being asked. If the question is put in such a way that you have to use least square parabola to approximate y for some s value, then after you've got the approximate value of y at that point, you are done. You don't have to spend time in finding or computing the summation of the square of the error if the question doesn't ask you to do so. It wastes of time.